MCV4U1, Chapter 1, Introduction to Calculus, Session 7. In this session, we are going to work on Section 1.3 from the textbook, Rates of Change. Let's go over the meaning of function and rate of change one more time. We know many practical relationships involve independent quantities. Examples: volume of a balloon varies with its height above the ground. Air temperature varies with elevation. The surface area of a sphere varies with the length of its diameter or radius. These and other relationships can be described by means of a function, often of the form of y equals f of x. The dependent variable y can represent quantities such as volume, air temperature, and area. The independent variable x can represent quantities such as height, elevation, and length. We are often interested in how rapidly the dependent variable changes when there is a change in the independent variable. Recall that this concept is called rate of change. In this section, we show how instantaneous rate of change can be calculated by finding the limit of difference quotients in the same way that we found the slope of a tangent. After this introduction, let's start with an example. Let's assume an object moving along a line would be a vehicle entering a highway and traveling north 340 kilometers in 4 hours. Usually, we consider an object is moving on a straight line, horizontally or vertically. The right side of the direction or upward is considered positive, and left side or downward is considered negative. In this example, the average velocity would be 340 divided by 4, which is 80 kilometers per hour north. We know average velocity is change in position divided by change in time. Delta S divided by delta T, when S represents the position of the object or vehicle on a straight line, and T is time taken. Let's assume a pebble dropped from a cliff 80 meters high. After t seconds, the pebble is s meters above the ground, where s at t equals 80 minus 5t2, and t is between 0 and 4. When t is 0, it is 80 meters above the ground, and when t is 4, it is on the surface of the ground. The question is, in part A and B, calculating average velocity of the pebble when t is between 1 and 3, or t is between 1 and 1.5. And in part C, it says, explain why your answers for parts A and B are different. Average velocity in part A is S3 minus S1 divided by 3 minus 1, which is minus 20 meters per second. And for part B, when t is between 1 and 1.5, it is s at 1.5 minus s at 1 divided by 1.5 minus 1, which is negative 12.5 meters per second. The reason that the answers are different is because of gravity. Gravity causes the velocity to increase with time. The smaller interval of 0.5 second gives a lower average velocity, as well as giving a value closer to the actual velocity at t equals 1. If we find the average velocity of the pebble between 1 and 1 plus h, when h is really small, the average velocity is the same as instantaneous velocity. S at 1 plus h minus s at 1 over h can be simplified as minus 10 minus 5h. H is not 0. We have an interval. H is the length of the interval. As h approaches 0, average velocity approaches negative 10, which is the same as instantaneous velocity. The instantaneous velocity when t is 1 is defined as limiting value of the average velocity as h approaches 0. Similar to what we've done in previous section, we want to find the instantaneous velocity at t equals a. We create an interval length h from t equals a to t equals a plus h, and we find average velocity. Delta s over delta t is s of a plus h minus s of a over h. The velocity at t equals a can be calculated by finding the limiting value of the average velocity as h approaches 0. The smaller h is, the closer average velocity and instantaneous velocity are together. Let's recap. Instantaneous velocity of an object with position function s at t equals a is denoted by VA, and it is limit of delta s over delta t as delta t approaches 0, and that is s of a plus h minus s of a over h, the limit of the average velocity as h approaches 0. Note that the velocity VA is the slope of the tangent line to the graph of ST at P, A, and SA. The speed of an object is the absolute value of its velocity. It indicates how fast an object is moving, whereas the velocity indicates both speed and direction relative to given coordinate system. Let's work on another example. Example 2. A toy rocket is launched straight up so that its height s in meters at time t in seconds is given by this equation. S at t equals negative 5t2 plus 30t plus 2. What is this velocity of the rocket at t equals 4? We find average velocity between 4 and 4 plus h and use the limit of average velocity as h approaches 0 and find instantaneous velocity. S at 4 plus h is minus 5h2 minus 10h plus 4d2. S at 4 is 4d2. Velocity at 4 is limit of the average velocity at 4, which is negative limit of negative 10h minus 5h2 over h as h approaches 0. This can be simplified as negative 10 minus 5h. Therefore, velocity at 4 is limit of negative 10 minus 5h as h approaches 0. And this limit is negative 10. As h is getting closer to 0, negative 10 minus 5h is getting closer to negative 10. Therefore, the velocity of the rocket is 10 meters per second downward at t equals 4 seconds. It is downward because of the sign of the velocity. Negative 10 means it is downward. Generally speaking, average rate of change of f on the interval a and a plus h is f of a plus h minus f of a over h as h approaches 0. And as you know, average velocity, average rate of change is rate of change over an interval. Instantaneous rate of change of f of x with respect to x when x is a is limit of delta y over delta x as delta x approaches 0, which is limit of f of a plus h minus f of a over h as h approaches 0, provided that this limit exists. If you put everything together, average velocity and slope of secant line are basically the same. Instantaneous rate of change at a point and the slope of the tangent line at that point have the same meaning. Example 3. The total cost in dollars of manufacturing X calculator is given by Cx equals 10 root x plus 1000. What is the total cost of manufacturing 100 calculators? This is not a calculus question. We are looking for basically C at 100, which is 10 square root of 100 plus 1000. What is the rate of change in the total cost with respect to the number of calculators, X, being produced when X is 100? As we talked about, cost of 100 is 1100, and rate of change in the cost at x equals 100 can be found as limit of c at 100 plus h minus c at 100 divided by h as h approaches 0. We find c at 100 plus h, which is 10 square root of 100 plus h plus 1000, and c at 100 equals negative 1100. Therefore, the rate of change would be limit of 10 square root of 100 plus h minus 100 over h as h approaches 0. To find this limit, we multiply it by the conjugate of numerator and divide by conjugate of the numerator. We use difference of squares, collect the like terms, and reduce the fraction by h. The limit would be limit of 100 divided by 10 square root of 100 plus h plus 100. This can be reduced by 10 as well. When h approaches 0, this limit would be 100 divided by 10 square root of 10 plus 100, which is 100 divided by 200, 0.5. Therefore, the rate of change in total cost with respect to the number of calculators being produced when 100 calculators are being produced is $0.5 per calculator. Limit of s at t minus s at 1 divided by t minus 1 as t approaches 1 is exactly the same as limit of s at 1 plus h minus s at 1 divided by h as h approaches 0. Therefore, to find average or instantaneous rate of change, to find instantaneous rate of change, we can use f of x minus f of a over x minus a as x approaches a. Instead of using a and a plus h in our previous formula, we use a and x. And we say x must be close to a. This is called an alternative form of finding rate of change. In example 1, S at t equals AD minus 5t2. S at 1 would be 75, and V at 1 would be limit of S at t minus S at 1 over t minus 1 as t approaches 1 if we use the alternative formula. This fraction can be simplified as negative 5 times 1 plus t, and the limit would be limit of negative 5 times 1 plus t as t approaches 1, which is negative 10. To find the limit, we find S at t minus S at 1, 5 minus 5t2. It can be factored as 5 times 1 minus t times 1 plus t. The limit is the same as limit of 5 times 1 minus t times 1 plus t over t minus 1 as t approaches 1. We reduce the fraction. T minus 1 and 1 minus t are opposite of each other. When we reduce it, we get negative 5 times 1 plus t. In general, the velocity of an object at time t equals a, VA is limit of S at t minus S at a divided by t minus a as t approaches 0. Similarly, the instantaneous rate of change in f of x, y equals f of x with respect to x, when x is a, is limit of f of x minus f of a over x minus a as x approaches a. These are called alternative formula for finding instantaneous rate of change. Let's recap. The average velocity can be found in the same way that we found the slope of the secant line. Average velocity is change in position divided by change in time. The instantaneous velocity is the slope of the tangent line to the graph of the position function, and is found in the same way that we found the slope of the tangent line. Very important to know. To find the average velocity, or average rate of change, from t to t plus h, we can use the difference quotient and the position function. Average rate of change is, average velocity is delta s over delta t, s at a plus h minus s at a divided by h. The rate of change in position function s at t is the velocity at t equals a, and it can be found using the limit of the quotient difference as h approaches 0. VA is limit of s of a plus h minus s of a over h as h approaches 0. Average rate of change of f of x when x is between a and b is f of b minus f of a divided by b minus a, and instantaneous rate of change of f of x at x equals a is limit of f of x minus f of a divided by x minus a as x approaches a. Next session we are going to work on exercise 1.3. Question number 1, number 2, number 3, number 4, number 5, number 6, and number 7, and also question number 9 and 12. Thanks for watching.